In this video, we're going to consider a model that looks at a dam failure scenario. Here, we combine at-risk with Precision Tree, a decision tree software package that enables us to construct a probabilistic risk assessment that models two dam failure scenarios. Descriptions of those scenarios are available in the model, and briefly what they are would be, the first would be an overtopping where water exceeds the top of the dam and causes erosion downstream of the dam. The second would be when the water rises behind the dam and causes a crack in a suspect joint or some other feature of the dam that results in an uncontrolled release of water. But let's have a quick look at the dam cross-section here and notice the elevations here in the vertical scale, because they play a prominent role in the models we're going to look at. They're basically showing you the elevation of the water. So here's 2,460 feet, still behind the dam, but above the spillway crest. Now let's look at our models. The first model is the lift joint slide model. This is the one that would result in the uncontrolled release because of the crack or weakness in the model, in the dam itself. Notice that we have four different elevations for the pool behind the dam. Water elevations that are below 2,462 feet, and then a water elevation from 2,466 to 2,467. You'll notice that these values have been estimated rather precisely. Up here in the function line, there is no uncertainty. These are point estimates, and that's because they are based on extensive amounts of flow data that are available from the dam. Notice that the same uncertainty bounds are found on the tensile strength being exceeded. This is the first event after the flow is determined. So here, if we take a look at this distribution on the yes branch, we find it's a uniform distribution between 1 and 10%. So this is basically saying that if we have a flow between 2,466 and 2,467 feet above mean sea level, there is a 1 to 10% chance that the tensile strength of the dam will be exceeded. If we look down here for the other flow ranges, we would find exactly the same distribution between 1 and 10%. So this event's probability is not dependent on the flow. Now let's move to the next event, cracks, uplifting, and sliding. This time we switch to the no branch here. And when we look here, we find the probability that you will not have cracking, uplift, and sliding when you have a large flow is between 1 and 12%, most likely a 5% chance. Now if we look at a lesser flow, we find the probability that there is no cracking, uplift, or sliding has increased considerably from 57 to 70%. Correspondingly then, you know that the probability that there will be cracks is decreasing. And then finally down here, when we have a flow in the 2,462 to 2,464 range, we see the probability of no cracking is quite high. It's between 99 and 100%. You notice the use of a lot of non-parametric distributions here, and that's because of the relative lack of data for these events. The tree structure gives our problem a nice transparency. It identifies three different pathways that lead to a failure. For example, here we end up with a failure. Here we end up with a failure. And it provides an estimate of the probability of each pathway. This times this times this equals this. And so this is the probability of a failure from this pathway. This is the probability of a failure for this pathway. For this introduction to the model, we'll only be interested in the annualized probability of failure from all three. So this number right here just takes the sum of this plus this plus this. Now let's look at the overtopping failure model. Here we have three ranges of flows of interest: less than 2,466 feet, over 2,467 feet. The key input to the model in this case is whether or not the downstream shell erodes. And we're going to see that the probability varies greatly. Here on the yes node, if the flows are over 2,467, let's take a look at this distribution. There's a 90 to 99% chance that the downstream shell will erode. However, if the flows are in this range, we see there's a 1 to 10% chance that the downstream shell will erode. Once we know that the shell has eroded, however, these probabilities do not change. The probability that the core wall will collapse is between 90 and 99%, regardless of what the initiating flow was. At this point, these values only depend on this value here. And by the way, you'll notice that these numbers are different. They come from the same distribution, but they are independent samples from that distribution. Likewise, if the core wall collapses, the probability that the upstream shell collapses and erodes is exactly the same. So this would be between 90 and 99%, just the same as this probability would be. So in this model, we have different probabilities here of the flow ranges. We have different probabilities here. But after that, everything else is the same. Once again, we have two failure modes. This times this times this times this gives me the probability of this failure mode. Similarly, this times this times this times this equals this is the second failure mode. If we add the two, we get our annualized failure probability. Let's run a simulation now on both of these scenarios. We're going to do 1,000 iterations. Let me start the simulation here. Now you'll notice that we are just estimating the probability of failure. The consequence of failure is going to be critically important in determining whether the probabilities of failure are tolerable or not. So here we just found that at a minimum there is 2 chances in 10 million that we would have an overtopping failure. We could have almost 2 chances in 1 million that we could have an overtopping failure. Someone must decide if those probabilities are tolerable. And the answer to that question would depend on, well, what happens if we do have an overtopping? While we ran that simulation, we were simultaneously running this simulation, and you can see this probability here. This is the minimum probability is about 1.6 chances in a million. The maximum is 1.4 chances in 100,000. So once again, someone will have to decide if these probabilities are tolerable, tolerable or not. But from this little model, you can take away that there is a very powerful set of tools out there that can be combined to help us do these probabilistic risk assessments.